Okay, so we'll just try a few more of these exercises. This time, kind of working the other way. And so I forgot what I said last time. I said bulls have a mean weight 2,400 pounds, standard deviation that I made up of 160. All right, and I'll say, how heavy is a bull in the 90th percentile? Okay, so I'll give you guys a couple minutes to work on this one. All right, do we have an answer here? $2604.8. Is that what we got? Maybe. Okay, great. So so in this case, just drawing a line. I'm kind of just drawing a line arbitrarily. All we know is that the area shaded to the left here is very close to 90%. Okay. So when I go to my table, what I'm not going to do is look up 0.90. Okay. We don't want that. What we want to do is we want to find the value closest to 90%. And that would be 0.8997, okay? There's 0.9015, 90% is in between these two numbers, but 0.8997 is closer, and so that corresponds to z equal to 1.28, okay? Because it's in the row 1.2 and the column 0.08. So z equals 1.28. This is the z that gives an area to the left equal to 0.8997, which is the closest value to 0.9, to 0.9 in the table. Okay, so we have this z-score. Now we have to turn it back into a weight. All right, so how do we do this? Well, we can say z is equal to y minus mu over sigma, and we can just plug in all the values that we have. Z is 1.28. Y is the weight that we don't know, that we're trying to find. The mean is 2,400, and sigma is 160. So at this point, it's just now a matter of solving for y. So 160 times 1.28 equals y minus 2,400. So I get y is equal to, something exciting is happening out there. So I do this 2,400 plus 160 times 1.28, 2604.8. And that is our answer. Okay. Are we feeling okay about all of this? Okay. There is a section called Assessing Normality, which is in the text, which is all about these normal probability plots. Basically, and this is sometimes called a QQ plot, and or a maybe a normal QQ plot. The QQ stands for quantile. And what that means is it's the theoretic quantiles versus the actual quantiles. All right, and basically what we're doing is we're just looking at data and we're saying if the data fit a normal model, what should their quantiles be, and is that the actual quantiles that we see in the data? Okay. You don't have to worry about the theory behind this. You can look at this. Just basically the main point is if if the data does follow the normal distribution, then the dots in the normal QQ plot will look like a straight line. Okay, that's kind of the key thing. Okay, so you should get something that looks kind of like this. Okay, maybe a little bit of scatter, but overall you should get a straight line if. So this is data that comes from data that fits the normal model. Okay, you know, if you sometimes you get situations like this. Sorry, let me just. Okay, and so this would be these would not be normal. Okay, so that's really all I want to say on section 4.4. And then I want to cover another section, which is jumping ahead to section 5.4, which is the normal approximation for the binomial distribution. Okay. So this is section 5.4. This is the normal approximation to the binomial. Okay, and so here's the thing, is that the binomial distribution, when do we use the binomial distribution? You know, when we repeat the same trial n times, and you know, every time you do it, you have the same probability of success, and you're looking for a certain number of successes. Okay. If you have a very large n, the binomial distribution ends up looking a lot like the normal distribution. Okay, so let me just let me see if I could find binomial distribution. Let's see. Let's see if this is the one I have in mind. Okay, so you know, we could say I'm going to flip a coin 4 times, and no, that's not. Okay, yeah, this is what I want. Okay, so here this is with n equal to 5 and p equal to 0.5. Okay, and here what it says is, you know, you have equal chance of getting 2 heads or 3 heads. Okay, and you know, if I just said I'm going to do this, flip the coin 2 times, okay, then I can get 0 heads, 1 head, or 2 heads, right? And so we can increase this, and we can also say, you know, if I want p is equal to 0.8 or something, then I'm more likely to get 2 heads or something like this. Okay, but I can increase. So this is if I'm going to flip the coin 20 times, and every time I flip the coin, I've got a 0.8 probability. You know, the most likely outcome is 16 heads, but 17 heads is also quite likely, and 15 heads is pretty likely. You know, but getting 2 heads is very unlikely if I've got a probability of 0.8 or something like that. Okay, and I can change it to 0.5. And here I've got this. Okay, 10 is the most common outcome. 10 heads, which makes sense, right? You flip the coin 20 times, it makes sense that you're going to get 10 heads. 11 heads and 9 heads are also common. But look at this. This looks a lot like the normal distribution, right? Okay, and And so we have a thing where we say, hey, you know what? Maybe I don't want to calculate all of these things, okay? I can kind of just approximate it with the normal distribution, okay? If I'm going to flip it 30 times, this looks, all of these things look a lot like the normal distribution. It's just getting a little bit skinnier just because the range here goes from 0 to 40, okay? And even, so, when I'm down to like 10, maybe it doesn't look as normal, or, if I only have 5 or something, it doesn't look as normal. But even with skewed distributions, like probability 0.8, if I increase this, okay, it's going to look more and more normalish, okay? Until a point where this looks pretty close to symmetric. It's not symmetric, but it's the amount of skew that we see. There is a little bit of a tail here, but it's quite small, okay? And so we can approximate this shape with a normal distribution, okay? So that's the idea that we're getting at here, is that we have a binomial distribution which says, what's the probability that I get 12 heads if I flip the coin 20 times, okay? We can do the numbers, the calculations exactly, right? If I ask something like, what is the probability I get at least 12 heads if I flip the coin 20 times? Could we do that with the binomial? Yes, but it would involve lots of calculations, right? To get at least 12, I would need the probability of getting 12 heads. I would need the probability of getting 13 heads, probability of getting 14 heads, 15 heads, 16, all the way up to the potentially getting 20 heads out of 20 coin flips, okay? And so that would involve, let's see, shading from 12 to 20. Let's go. Okay, I would have to go from here all the way up to there, right? So it would involve getting all of these to the right, and that would be, quite a few calculations, which would be rather tedious to do by hand. Okay, does that make sense? Okay, there is kind of I have to preface this, which is basically, if you have a computer, then doing these binomial calculations by hand, or not quote by hand, doing these exact binomial calculations, even if there's 50 of them that you have to do, is not bad. It's very quick to do on a computer. But if you want to get a ballpark number by hand, then you don't want to have to do this, all of these tedious calculations, and we can approximate it with the normal distribution. All right? Is this okay? All right, so normal approximation to the binomial. This, we do this if we want to estimate binomial probabilities. By hand. Okay, and especially when the actual binomial calculations would be too tedious. But if you have access to a computer and you're willing, or if you just want it done on the computer, or if you have the internet, you can just probably look up Binomial Distribution app and it'll have some kind of calculator for you. If you have a computer, it's very quick to do it. There's no sense in doing this. Okay, but so basically when n times p and n times 1 minus p are both bigger than 10, or greater than or equal to 10, then the binomial distribution looks a lot like the normal distribution. So basically you just need n, your sample size n, just needs to be large enough so that both n times p and n times 1 minus p are greater than or equal to 10. So n needs to be, fairly large. Okay? So, here's an example situation where we might want to do this, all right? I will flip a coin 50 times, okay? And someone says, you win the game if you get over, I don't know, 35 heads or something. Maybe that's too unlikely. Let's see. Okay. Yeah, well, okay, we'll say 20 heads, 33 heads or more. Okay. So I will flip a coin 50 times, and I will win if the coin lands heads 33 times or more. Okay? So what is the probability I win? Okay, and this is a fair coin, which means probability of heads is 0.5. Okay. So 33 times or more means, to answer this with the binomial, we would have to do what? We would have to do 50, choose 33, etc., 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 plus 50, choose 34, plus 50, choose 35, all the way up to what? 50, choose 50. Okay? So there, this is like, this is too many to do. There's 18, I think, if you count them up. We don't want to do that. Okay? So we can, so this would, this involves 18 calculations to do. Okay? This is too tedious. Okay, so instead, we are going to do the normal approximation. Okay? And so, I'm gonna cut this picture here. Okay, so this is what the binomial distribution looks like. Okay, and we're going to approximate it with the normal distribution. So where's my little diagram? I'm going to draw this also. How do I scale this the other way? Oh yeah, this is what I want. Okay, so we're gonna try this. Okay, so basically, this is the binomial, and this is the normal approximation. Okay, so what I need is I need to know where's the middle. Okay, so where's the middle of our binomial distribution? That's going to be the middle of our normal approximation. It's at 25, right? And I can see it on this diagram here, but if we didn't have the diagram, we do know that the mean of a binomial distribution is what? N times p. And do we remember what the standard deviation of a binomial distribution is? Yeah, it's the square root of n times p times 1 minus p. Okay? So in our case, 50 times 0.5 gives me 25, so I get that. And then the standard deviation is going to be the square root of 50 times 0.5 times 0.5, which is something else. Square root of 12.5, which is 3.535. Okay. All right, so this is my standard deviation, and so my normal approximation will have mean equal to 25 and standard deviation equal to 3.5355. So I'm going to use the mean and standard deviation of the binomial distribution as the mean and standard deviation of our normal approximation. Does that sound good? Okay, and so now the question is, all right, I said I want 33 or more heads, right? So, I want 33, 34, 35, 36, so on and so forth, okay? So, we might think that I should draw a line at 33. But I don't, okay? I have to take into account, so if we look at these bars, and if I were to zoom in here, and maybe I can I zoom in? I don't know. So if I zoom in, and if this is the bar that represents 33, okay, and if it's centered at 33, let me see if I can just chop this little piece here. Okay, so we're gonna just zoom in on this little piece here. Where can I put this? Okay, so I've got a little bar here. So this one is 31, this is 32, and this is 33. You know, the bars are centered at the numbers. Where am I actually shading, starting to shade from? At 32.5, right? Because if I drew my vertical line at 33, I would be missing half of this bar here. Can we see that? Okay, so I don't draw it at 33, I actually draw it a little bit to the left of that, and so my cut area, my cutoff, is at 32.5. Is that okay? And this adjustment only applies for the normal approximation to the binomial. It's called the continuity correction. I guess it only applies when you're, so if the binomial is discrete, right? You can only have certain outcomes. You can only have 16 heads or 17 heads. You can never actually have 16 and a half heads. And in our case, we're trying to approximate this discrete thing with a continuous thing, and so this is known as the continuity correction. Okay, so we cut it at 32.5. So my z is going to be 32.5 minus the mean of 25 divided by the standard deviation of 3.5355. Okay, so on my calculator I'm going to do 32.5 minus 25 divided by, and I'm going to just plug in the standard deviation that's already in my screen here using the answer key. And so I get a z-score of 2.12. So z is equal to 2.12. Is that okay? And then I want the area to the right of 2.12. So what is the area to the right of z equal to 2.12? Well, I would go to my reference table, and I'm going to just find the area to the left of negative 2.12, and I get 0.0170. Okay? Or I could find the area to the left of positive 2.12 and subtract that from 1. But I can also do, because I want the area to the right, area to the right of positive 2.12 is same as the area to the left of negative 2.12, which is 0.0170. Okay. So what is the probability that I win this game? Okay, flipping a coin 50 times, you win if you get 33 or more heads. I have about a 1.7% chance of winning. So not very good, not a very good chance of winning. Okay, and here the online calculator says the exact probability according to the binomial is 1.64. Okay, so this compares favorably, compared to exact probability of 0.0164. Okay, so the normal model does a pretty good job of approximating it. And actually, if it's probably even closer. Okay. How are we feeling? Is this okay? The normal approximation to the binomial? All right, and so whether you go, sometimes in some situations you would go to the side above. You would add 0.5 to it, or you would subtract 0.5. Okay, so a lot of times I like to just kind of draw a picture, like do I add 0.5 or subtract 0.5? Okay, so let's let me just let's try something here. Okay, and so this is not a situation where we would use the binomial approximation, but I think here we can get some good insight as to where we should draw our cutoff values. Okay, so in this case, n times p is not over 10, so we would not use the binomial or normal approximation here. Okay, so in this in this scenario, we would not use normal approximation. Okay, because n is equal to 10 and p is 0.5. Okay, but here we can get some insight as to when we would say. So where would I cut? Where is my cutoff? If the question is what is the probability of getting at least 7 heads? What is the probability of getting at most 5 heads? Okay. What is the probability of getting between 3 and 6 heads inclusive? Okay, so these are all, so you have to imagine, okay, what is the probability of getting, I guess I'll let you guys finish copying these down. So if I wanted to ask what is the probability of getting at least 7 heads, where would my cutoff be? So I want to include 7, 8, 9, and 10, right? So I want to include the bar for 7. So that means my cutoff should be 6.5. Okay? What is the probability of getting at most 5 heads? What does it mean to get at most? That means up to and including 5, right? So I would go 6, so I'm sorry, for this one I would go 6.5 and shade to the right. For getting at most 5 heads, I want up to and including 5. So where would my cutoff be? At 5.5, and I would take the area to the left, right? So I would get 5.5, and we would take the area to the left. Is that okay? All right, and then getting between 3 and 6 heads, where would I go? From 2.5 to 6.5, right? Because we want to include the bars for 3 and 6. So we would go 2.5 to 6.5. Are there any questions on this? Okay, so that will oh, okay. And I want to mention something. In the textbook, they have an alternate formulation for all of this, okay? I do it with where we deal with the counts. Mean is n times p, and the standard deviation is the square root of np times 1 minus p. But they also have one where, you know, we're looking at the proportion, okay? These questions could be asked, the exact same questions could be asked in a different form, which is, I'm going to flip the coin 10 times. What is the probability that at least 70% of the flips are heads? Okay? That's the same question, right? Here, this one says, what's the I'm going to flip the coin 10 times. What's the probability of getting at least 7 heads? I could say, I'm going to flip the coin 10 times. What's the probability that it lands heads 70% of the time, or at least 70% of the time? These are the answers would be exactly the same. They've just been asked in a little bit funny way, or a little bit different ways, because 70% of 10 is 7 heads. So I don't like to do calculations that way because the continuity correction gets really ugly trying to do things that way. So I always like to deal with counts and doing the continuity correction, because the continuity correction when you're dealing with counts is always going to be add 1/2 or subtract 1/2. And when you're dealing with the percentage straight up, things get a little bit messy. So, if as you're reading through the textbook, don't worry about it. Okay. Man, I think there's people think something's going on. We're having a class in here, guys. People are screaming out there. Something is happening tonight. Something is happening. Definitely missing out on something. Okay. All right, is that okay? All right, I'm going to put a break in the video here.